This webinar will look at some basic calculations in linear algebra implemented in Maple in a syntax-free way. The goal being to show first how Maple enhances the teaching, learning, and doing of these calculations, thereby generating greater insight than is usually associated with pencil and paper technology. And second, the syntax-free approach means that the tool does not get in the way of the math. Gaussian elimination is an essential part of the toolbox in linear algebra for any student or any user. Let's solve a system AX equals B implementing Gaussian elimination with various Maple tools that one could use. We'll hit this hyperlink and go to a page where we have room to solve the problem. We'll begin with an interactive solution using the context panel. I want to load the student linear algebra package, so tools, load package, student linear algebra. Then we need A and B, the matrix A, the vector B. Here's one way to do it. Select A, hold down the control key, and pull A over. That's called here a control drag. It's not a Maple thing. It's a Windows thing, and I understand it can be done in other operating systems too. Put a comma, and do the same thing with B. It's equivalent to copy paste. Now let's go to the control panel, conversions to augmented matrix. And since we're going to reference this more than once, let's give it a name, assign to a name, and I'll call it AB. Now that we can reference it, let's type AB and do a control equal. Now a control equal is equivalent to this evaluate and display in line. An alternate to control equal, which is what my fingers are trained to do, is Alt Enter. Or you can click on that context panel item. Okay, so now we go to student linear algebra, solvers and forms. You see row echelon form. Let's pick elimination only. Okay, so we have an upper triangular matrix. Back substitution would get us a solution. So let's go back to student linear algebra. Solvers and forms. Row echelon form. Back substitution. Okay, so there's the solution to this system. Alternatively, we could just go directly to the reduced row echelon form, student linear algebra, solvers and forms, row echelon form, reduced. So the fourth column is that solution, and if you wanted to get your hands on that fourth column, go to select elements, restrict columns. In this dialog, you type 4, and you pull out the fourth column. So we've just shown how you could get a solution quickly, efficiently, using a tableau that's familiar to the student who's learning this material. There is a tutor. Now, what's a tutor? Let's go up here. Tools, tutors. These are 50 some odd pop-up tools. We go over here to linear algebra. You see there are a collection of tools. I'm going to make use of one of them, and I will access it through the context panel. So I type AB, control equal. Go here to student linear algebra, tutors. Whatever tutor applies to a matrix like this can be accessed. We want Gaussian elimination. So this dialog comes up. This is what the kind of a pop-up tool I'm talking about. Here's the matrix. Now, Maple doesn't know that this is an augmented matrix, so we have to tell it. And to tip off, Maple sees it as the matrix of a homogeneous system, 3 equations and 4 unknowns, shows here. If you click this augmented box, then Maple uses 3 variables, 3 equations and 3 variables, puts the equal sign in, and this stroke is the place where the equal sign would go. Now, we can perform the steps of Gaussian elimination using these buttons to perform elementary row operations. Now, if I were doing this particular problem by hand, I would add row 3 to row 1, creating a 1 in the 1, 1 position. So I want to add 1 times row 3 to row 1. And I now have a 1. Makes it easier to zero out the 8 right under the 1. I want to multiply row 1 by -8. So I'm multiplying row 1, and I want to add that to row 2. So I've just made a first 0. Rather than bore you with all of that computation, I'm going to tell Maple to take the next step. So we have the second 0, and Maple is telling us up here what it takes to do that. Then I'm going to tell Maple to finish the job, take all the steps. So now I have an upper triangular matrix. And what am I trying to do? I'm trying to solve the system of equations. So I say, let's solve the system. And in this dialog, I ask for the equations. And I notice the bottom equation is easily solved for x3. So we solve that one for x3. Now, if I know x3 and I put it into the middle equation, I could then solve for x2. And if I know x3 and x2, I could put that into the first equation and solve for x1. And if I tell Maple to display the solution, then I see, okay, this is what happens if you do Gaussian elimination to an upper triangular matrix and then do back substitution to get the solution to the set of equations. Upon close, I get the final result. Notice that all we got back from our work in the tutor was the final result. The steps we went through are not recorded. So here's a way to do a stepwise solution of Gaussian elimination in such a way that you can record or have a record of the steps. If you make use of the context panel here, go to Student Linear Algebra. You see you have the option elementary operations, and you have a row operation of addition, multiplication by a scalar. You can do a pivot on that row, swap 2 rows. When you do one of those calls, you get a dialog, and here I just did a copy paste of what the dialog would look like. It looks like what happened in the tutor. Use it the same way. Tell Maple what you want to do. Say OK, Maple will do it. And these computations are then written to your worksheet, and then you have a record of how the computation was implemented. Let's try a little bit more challenging problem. This one right here, number 3. I want to project this vector C onto the plane spanned by vectors A and B, and A and B are defined right here. And there are a variety of ways to do this. In fact, the student of linear algebra who's gone through a multivariate calculus course would already have seen a method to do this. Project C onto and orthogonal to the normal to the plane. And normal to the plane is easy to find, A cross B. Another way is to construct a projection matrix to project onto that subspace, that two-dimensional subspace. And the toughest way for, I think for students, I found this difficult when I was first learning it because I couldn't visualize it. Minimize the distance between C and a vector in the plane. And without drawing those vectors and seeing how minimization of the distance leads to a projection, I just found this approach difficult. So click this hyperlink, take us to a page where we can work this problem. The first thing we want to do is define the vectors. Now, one way to define the vectors is to use this matrix palette. There's dynamic choose symbol, lets us select the size of the matrix or vector. So here's a template. We want this to be C, so it's 3 tab negative 4 tab 8, and then give this the name C by assigned to a name in the context panel. Let's see. And so here's the vector C. Now here's another way to define a vector. Use inequality symbols as angle brackets. So let's do A, which is 2, 3, negative 4. And I will assign that the name A. So assign to a name A. And then we need to do B. I'll do the same thing with angle brackets. B is 5, negative 7, 1. And this time what I'll do is I'll do a control equal so you can see that I've actually defined a column vector, and I'll give that the name B. Assigned to a name B. There's a task template that will let us do this projection. Now, what's a task template? Tools, tasks, browse, table of contents. This is 349 pop-up tools, embeddable tools for doing stuff in Maple. Right now what we want to do is go to Linear Algebra, Visualizations. We see Projection onto 2D. So here is the test template. It can be embedded by clicking one of these two buttons. Default content means you get the extra verbiage. Minimal content means you get enough to make the thing work. And I've got the template already embedded. You can see I've written down the path to it. Okay. Vector to be projected, C, because it's been defined. Basis for the plane, A, B. Projection into the plane. Projection, the orthogonal component. And the graph that you really wish you would have on the board, but the graph on the board can't be turned like this one. So this gray hash mark stuff is a piece of the plane defined by these two blue vectors. That's A and B. Notice the blue coloring here. The vector to be projected is C, that's in black. The green vector is the component in the plane. The red vector is the component orthogonal to the plane. I could use these three colors here, but this vector is black. I don't think I could color this black. I would lose the sight of everything. The solution that the linear algebra student who's done a course in multivariate calculus would be this one. You need a normal to the plane, which you could get by doing A cross B. Now I've already typed in A cross B. Where did I get that cross symbol from? Cross product symbol here is in my favorites palette. Your favorites palette may be empty. How do you populate a favorites palette? Well, you find symbols that you use frequently, like a cross product, del operator, dot product, and you right click on that item and you add it to your favorites. Okay, so I've got A cross B. If I simply use the context panel to say assign that name, Maple will calculate the cross product and assign it to n. And I've done the same thing here with the projection. C dot n over n dot n, n. That projects C onto n. I've called it Cn. I've pre-typed it so that you don't have to watch me do all that typing. Assign name. Okay? What is the component orthogonal to the component along the normal? Because that's what this is, component along the normal. The projection into the plane is that component, so that's C minus Cn. I believe that vector is visible here on the screen, this green vector. And just to show you that n and Cn were actually computed by Maple, there's n and there's Cn. This is actually Cn, the component along the normal. Remember how we color-coded that? That's the component along the normal. You might see here my use of vectors as bold Roman, but when I type them first on the keyboard, they come out in italics and they're not bold. Since I like bold Roman, I just simply use these toolbar buttons to make them bold Roman. I find that easier than trying to put arrows over the top of things. The notion of a projection matrix is certainly something pertinent to a linear algebra course. So let's get a projection matrix directly in Maple. We're going to load the student linear algebra package. So tools, load package, student linear algebra. We need a list of the vectors a and b. List take square brackets, a comma b. If we go here to student linear algebra, constructions, Maple sees this list and says, oh, you probably want to make a projection matrix. It makes that matrix. I'm going to give it the name P for projection. Then I'm going to use that projection matrix to get the two components, the projection onto the plane, P dot C. That's that vector, and I believe we've seen it before. And the difference, C less P dot, that's a period, but non-commutative multiplication, C, that's that vector. Can we get all of that on the screen at once? That's a challenge. Let's close this. I wonder if you can see it. No, you can't see all that at the same time. But look here. 5 over 26, 73 over 26, 5 over 26, 73 over 26. Well, what's the recipe for creating a projection matrix? Well, what you find in the literature is something like this. M here, which is a matrix whose columns are the vectors that form a basis for the subspace. You pretty much want the vectors to be linearly independent, not just a spanning set, but a basis for the subspace, so that this product, M transpose M, is then invertible. Well, we need to form that matrix M. So we need a list A comma B. We're going to combine that into a matrix by going here to select elements, combine into a matrix. There's the matrix, that's M. So give it the name M. And now this recipe can be implemented in Maple. Period for non-commutative multiplication. Percent T is the transpose operator. Minus 1 as a power will be an inverse operator. So drag this down, hit the enter key, and we have a matrix which should be the same as, let's just hit the enter key, as the projection matrix that Maple created. And if you quickly scan these two matrices, you see they are the same. Finally, let's turn our attention to this approach to a projection via minimization of an error. So first I want to draw a picture. This picture is dynamic. The vector n is in red in this diagram. The plane spanned by A and B is this colored portion here. A arbitrary vector in the plane is this green vector. C is in black. And the vector from the plane up to the tip of C is this gold vector. What we're trying to do is move this green vector around in the plane so that this gold vector is as short as possible. Now, the vector in the plane is a linear combination of A and B. So AA plus BB is that green vector. How can I move that vector around? How can I vary A and B simultaneously so this vector moves around? Well, here's one way to do it. This is a portion of the AB plane. As I select points in the AB plane, I'm picking values of A and B. As I pick these values of A and B, you can see here what those values are. Here is the vector in gold. This is the gold vector, and here is its length, and I'm trying to minimize that length. If I stay down here, the numbers are big. If I go up here, the numbers start to get smaller. And now I've got a 5,9. There's a 6. I go back. Maybe I can get a 5,9 again. Oh, how did I get that 5,9? Okay, but you can see that by making these choices of AB, you can change the length of that gold vector There's a 5/8. Okay, that's pretty small. And you see visually that as you minimize the length of that gold vector, you are getting a projection. You can look at it this way. The projection, we move that over a bit. You would bring C out a little bit, the green vector out a little bit more. This would be more upright. So here's a tool. You play with it and you realize minimization of the error is going to end up with a projection. Finally, let's turn our attention to the computations implied by that visualization. We'll begin with the vector, the screen vector in the plane, linear combination of A and B. A space A plus B space B, space being implied multiplication. And I want to give that vector an equation label. So by hitting the enter key, it picks up this equation label 3. The difference, the goal vector, is C minus that vector. So C minus, why don't I just use the equation label? So to do that, Control L 3, that's the goal vector. Now this equation label 3 can actually be changed by right click, label reference, and you can actually then see what you subtracted because the label number stands for the thing labeled. At any rate, this now, the goal vector now has an equation label. We want the length of this vector. So standard operations, norm, Euclidean. That's what we want to, that's the algebraic expression we want to minimize. It's a function of two variables. It will help if it has a name, so we'll give it the name F. And now we can apply the techniques of the calculus, just differentiate with respect to A and B. So we have differentiation operator here, partial derivative, partial with respect to A, we'll tab over, we'll put F equal 0, comma, partial derivative with respect to B, B, tab F equals 0. Those are the equations we want to solve. Well, there's a solve command here in the context panel. Take the simplest solve. We have the values for A and B. Be interesting to see what they are as approximate numbers. Okay, so you can see the values that we should have ended up with in this visualization. But how do we get these numbers into the green and gold vectors? Well, we're going to use this evaluation template. Now, you'd find it in the expression palette. It's down here. I've put it into my favorites palette. The vector here is the green vector, Control L3. And we want to evaluate that at this set of equations. So Control L8 and remove the extraneous equals A. And you notice the 5 over 26. I just did it again here for the goal vector. It had equation label 4. Tab down here, Control L8, Control equal, and remember 73 over 26 is the component orthogonal to the plane. Another concept in a linear algebra course is the notion of B squares. So here's a problem. B squares fit this quadratic to these 4 data points. So do that. We'll work over here in this hyperlinked worksheet. We'll begin by getting the appropriate data into Maple. I've typed here a list of the x-coordinates of these points, 0, 2, 4, 7, and here a list of the y-coordinates, 1, 4, 6, 9. I want to give them the names, x and y respectively, so assigned to a name, I use uppercase X for the x-coordinates, and over here assigned to a name, uppercase Y for the y-coordinates. Now, we want also a list of points. Now, points are themselves lists, so I want a list of lists. To do that, I will make the generic list x sub k, comma y sub k. And I'll go here to sequence in k, from 1 to 4, so there's a 1 there and a 4 here. And then I want that to be a list, so conversions to list. And then I want to give that a name so I can reference it, assigned to a name, and Q is an easy letter to find on the keyboard. So I have 2 different ways to reference the data. Then I want the function. So I want it as a function. So I'm going to control drag the whole thing, f of x equals, and simply go up here to assign function. And that takes care of all of the work of assigning this rule to the function name f. And then I will load the student linear algebra package. Tools, load package, student linear algebra. If I substitute these 4 data points into this function, I'm going to get 4 equations and 3 unknowns. So I have overdetermined equations. So what will these equations look like? Well, the generic equation is f of x k equals y k. I want a sequence of those. So again, let's go to sequence in k, 1 to 4. Need that to be a set. Conversions to set. And then I want to give it a name. How about EQ for equations? EQ. Now, get that into something in linear algebra that will do least squares. So here is EQ, set of equations, and here is the set of variable names, which are A, B, B, C. If I go here to student linear algebra, least squares. That's about the only thing that can be done here. Now, if there is a free variable, Maple will use this name, underscore T, and it will subscript that, 1, 2, 3. It's kind of messy looking. So I'm just going to put the letter S. But there is no free parameter. Maple calculates A, B, and C and displays those values here in this set of equations. To get those into the function f, let's do a substitute into, and we'll substitute into f of x. So here is the least squares quadratic that best fits these 4 data points. Now there is a curve fitting tool. It used to be called an assistant. Well, I guess it's still called an assistant, but they had it up in here with the assistants. It's not there anymore. It's down with the tutors in statistics. You can access it through here, but if you do that, you've got to get the data in somehow, and I think it's much easier to get the data into this assistant through the context panel. So, still called an assistant. Q is the list of lists. When Maple sees that list of lists, curve fitting, interactive curve fitting, variable is X. This is the curve fitting assistant that already has the data in. You can see Maple drew the 4 points. Down here we're doing least squares, so if you type f of x, Maple knows what that function is, overwrites that default linear function. So you draw, click that button, you get a plot. You see the least squares curve drawn and the data points, and here is the fitting function. Now, when you're done, and you click this done button, you can return this interpolant, or you can return the graph. Now, since you can draw the graph from the interpolant, I always return the interpolant. Now, if you want to draw that graph of points and fitting function, you can do it this way. Here's Q. These are the data points. If you go here to plot builder, you get this pop-up that says, oh, you want to plot these points. Yes. So in options, you can make some nice changes here. The window at which this will be drawn. Well, if you look at your data, you see probably you want to do -1 to 10 here and have Maple put an X on that. What happened over here? There's the minus, and somehow I lost the 1. Down here, 0 to 10, and you have a Y on that axis. The symbol, I like a solid circle, so solid circle. I like them bigger than the default size, so try a slightly bigger size. And you can do a preview here. You can see, oh, that's going to look pretty good. Okay, so then you click plot. And then to get this onto the graph, just control drag it onto the graph. And now you have the same graph that was in the assistant, and you've constructed it yourself. Now let's move on to a solution from first principles. We can form the sum of squares of the deviations. So here I have a summation symbol. It stands for sum function. It comes out of the expression palette. I've got it in my favorites palette. I like k as my index, k from 1 to 4, and I just use the tab key to move around. And I need squares of the deviations. And what are the deviations? What do they look like? Well, it's f at x k minus y k. And I'd like to give that a name, so I'll give that the name s is simple enough. Okay, sum of squares. So what is that sum of squares? That's what it looks like. This function of ABC needs to be minimized. You can do it numerically. Through the context panel, let's go down here to optimization, minimize, and you get ABC calculated numerically. This is the sum of squares. How would you do it analytically? Well, you write the normal equations. You take derivatives. So let's go here to the calculus palette. We've seen something like this earlier. Partial with respect to A, S. Now whether you put equal 0 or not, Maple assumes that you meant it. So I'll just do B, S. And one more derivative, C. Oop. All right, those are the equations to solve. There's a solve. The simplest solve should do it. I want to get this data back up into function, and maybe even into S. So I can do a substitute into here to get that into function f of x. I think that's the same as we had obtained here. With equation label 5, you want to compare that to equation label 5. Control L for equation label 5. And you can see that they are the same. If you want to see how big the value of S is, I think you could do the same thing. You could, well, you would have to go back up here to this set, or we could use this template. It's S we want to evaluate using equation label 9, I believe it was. What is the that number as a floating point approximation? 068, and I think our numeric value here was 068. Now all of this stuff that we've just gone through is well and good. It helps to tie two existing knowledge in the user's head, but we want to examine this problem from the point of view of linear algebra. Matrix formulation of the problem. Okay, so we had four equations and three unknowns. Get that straight. 4 equations and 3 unknowns. Okay, overdetermined. Right? In a matrix formalism, we would be solving a problem of the form AU equals Y, where U, the vector U, is the parameter vector ABC. Now, how do you do this? Well, you multiply through by A transpose. So A transpose A is the matrix M. So you have MU equals, and A transpose Y is B. And that's what we would like to do. So what we're going to do, instead of having two sides, a left side and a right side, what we're going to do is we're going to write an augmented matrix, A comma Y. And so we multiply that by A transpose. It will end up giving us MB. So we had equations, EQ. Let's go here to linear algebra, constructions, generate matrix. We want the augmented form, and the unknowns are A, B, C. Okay, so this matrix is the augmented matrix, and I'm going to call that AY, for want of a better name, AY. However, we also want just the matrix A because we've got to have A transpose. So we'll pull A out of AY. So here's AY. And I'm going to just grab the first three columns. So select elements, restrict columns. I want 1.3. And I'll give that the name A. Okay, so now I can multiply the augmented matrix AY by A transpose. So it's A, and you got to use %T, period AY. If we row reduce this, we should be able to pick off the solution. So linear algebra, solvers and forms. Let's go row echelon, and let's just pick reduced. This last column, this fourth column, is the vector of solutions U. So to pick that off, you could go here to select elements, restrict columns. We just want the fourth column. Now there's a checkbox here, and that checkbox returns that fourth column as a column vector, not as a one-column matrix. Now, in linear algebra text, this distinction between a one-column matrix and a column vector is blurred. You flip back and forth, whatever the context requires. But you're in a structured computer algebra system. You've got to be careful of making distinctions between data types. I guess I got to hit OK here before I do anything else. Okay, this is the thing I want to call U, so I'll assign to a name U. Now, how do you get U into the form A equals this, B equals this, C equals that, so you can do a substitute into? Well, here's a way to do that. Make a vector, A comma B comma C, put a comma, put U. Okay, so what you want is A equals this first component, B equals the second component, C equals the third component. But if you go here to equate, Maple will form the equations A equals B equals C equals. And now you can do a substitute into, and if you substitute into f of x, I believe you will get the same thing that we had. We had was equation label 5, if I remember correctly. Okay, you get the same fitting function that we've seen several times before. The simultaneous diagonalization of two matrices exposes the user to some very interesting linear algebra. So here in problem 10, I have two matrices, and I want to find a transition matrix S for which S transpose AS is diagonal and S transpose BS is the identity. This is not a similarity transform because this is not S inverse. Part B goes on to examine the connection between this problem of simultaneous diagonalization and the solution of the generalized eigenvalue problem, where it's no longer A minus lambda I x equals 0, but A minus lambda bx equals 0. So let's hyperlink over here to a worksheet where we can actually do these calculations. Here's the algorithm that I'm going to use and implement. I'm going to get the Cholesky decomposition of B. That decomposition is of the form B equals L transpose, and L is a lower triangular matrix. Then I form this matrix C. Turns out it's symmetric. L inverse A L inverse transpose. I then get the eigenpairs of this matrix C, and the eigenvectors are normalized. I form a matrix of these normalized eigenvectors. The matrix S that I want is L inverse transpose M, where here is M. And it will turn out that the columns of this matrix S are these generalized eigenvectors, and they satisfy this equation, A minus lambda bx equals 0. So that's the algorithm we want to. The solution is implemented by following through these steps. So the first step is to get some data into the problem. We need the linear algebra package. So tools, load package, and I'm going to go here to linear algebra. Okay, then I need the matrices A and B. So let me close this for a second so I can grab the matrices A and B. I think if I grab A equals and drag it down here, I can just do an assign name, and B equals assign name. Now, we need that A and B are symmetric, and I think you can see that A and B are symmetric, and we need that B is positive definite. We're going to check that. So B is this matrix. We'll go to the control panel here, queries, is definite, positive definite, and Maple says yes, it's true. And you can check that by looking at its eigenvalues. Now, Maple will solve this problem directly, comma B. Make that sequence. If you go here to eigenvalues, etc., we'll just here pick eigenvalues. We get back the two generalized eigenvalues of this problem. Here you see roughly, this one is what, 4.3, this one is -1. So let's get this matrix L. It requires the Cholesky decomposition of B. So B colon equals solvers and forms Cholesky. That's the matrix L, assigned to a name L. And if you want to verify that L transpose is B, we can do L period for non-commutative multiplication, L percent T, up percent T. And that appears to be the matrix B. Step 2 requires us to obtain the matrix C, obtained by using L. So this is the maple syntax for computing this product. I think rather than have you watch me struggle to type that, I'm going to control drag it, control equal. We have a matrix that we are going to call C, assigned to a name C. Okay, so that was L inverse A, L inverse transpose, and you can see L inverse transpose and L inverse here. In step 3, we obtain M and then S. Okay, so from C, we're going to get M. How do we do that? C. We need the eigenvalues, eigenvectors of C. So eigenvalues, let us pick eigenvectors. So here are the eigenvalues. We recognize them. We had them a minute ago, 4.3 and minus 1. And this matrix, which we want to grab, so we can do a select element 2 that singles out that matrix. We want to split that into columns because columns are vectors that we need. So select elements, split into columns. Then we want to normalize these vectors. So normalize mapped onto these vectors in a Euclidean normalization. And then these columns, these are the vectors V, V1, V2. Right? We want those put back into a matrix, and that matrix we call M. So combine into a matrix. Select elements, combine into a matrix. This is what we call M. It might be nice to try simplifying that. Yes, it's so much nicer if we get a simplify on that. But that's what we're going to call M, so we assign that to a name M. And from M, we construct S, and the construction is L inverse transpose M. And the way to do that in Maple is just use percent T for the transpose and a period for non-commutative multiplication. So this matrix looks like that. I wonder if a simplify would help that. I'm going to try. I'm going to try simplifying that. Simplify. Yes, it's much simpler. And that's the matrix S. So let's call that S. Well, we've come up with a matrix S. Does it do what it's supposed to do? Is it true that S transpose AS will be a diagonal matrix with the generalized eigenvalues on the diagonal? So how would we do that? S to the percent T. Oop, came down too far. Period. A period S. Well, that's the appropriate diagonal matrix. And what about S transpose B times S, giving us the identity. So it's S to the percent T, period B, period S, identity. Are the columns of S the generalized eigenvectors? Okay, here's S. We want to grab its columns. So where is it? Select elements, split into columns. So here are the columns. And I'm going to give this list the name uppercase X, so I can refer to X number 1 and X number 2. And what we want to check is A minus lambda 1 B, that matrix is an annihilator for X1. So let's see what we have to do here. A minus, now that first lambda is 43 over 10. So 43 over 10. Oh, closed it too soon. We need B. Now we can close that. And we want to multiply that, so period for multiplication, X1, 0 vector. And we do the same thing for the second eigenvector, A. Now that's minus 1. So minus and minus 1. When I just A plus B, it's a little simpler there, times a period there, X2, 0 vector. Now all of these matrix computations that we've done, these vector matrix manipulations, they're hidden forms of just formulating and solving appropriate equations. So for example, suppose S were completely unknown, A, B, C, D, and lambda, the diagonal matrix, UV, the two generalized eigenvalues. When you form this matrix, S transpose AS equals lambda, you're getting 4 equations. And when you form S transpose BS equals I, you're getting 4 more equations. So you have 8 equations in 6 unknowns. If you throw that into Maple's solve command, you will get these solutions. And if you take the trouble to check, they differ only in the ordering given to the names A, B, C, D, U, V. So brute force solution, verifying that all you've really done has been to find solutions to a set of equations. Let's take a look at this Jordan form calculation. We'll put this matrix A into Jordan form. The intrigue that it has for me is, well, way back when I was taking a linear algebra course at Rose-Hulman Institute at New York University, had Louis Nierenberg for the course. The way things went in the 50s when this was taking place, early 60s, they wrote on the blackboard and you copied down notes. Well, there was a little book, Russian author, translated, Gelfand. Louis Nierenberg was using color chalk to describe how some of these basis vectors float around here, there, and everywhere. He ran out of colors after a couple of colors, and he turned to the class and he says, well, you know what I mean. Well, I didn't know what he meant. And I spent a lot of time trying to figure out what this Jordan form stuff is all about. And in the textbooks I was reading at the time, it was very abstract algebra. And it put me to the test, right? Until I dug in and saw something that I can get my hands on. And that something really is tools in Maple that allow you to see stuff that I don't know. I had a major my first chair when I first took a job after my PhD, who claimed that students could learn from the general to the particular. Right? So you do this generalized theory and then you give them an example. I never found a student in any of my courses ever who could do that. And I can't do that. So that's the interest that I have right here in this Jordan form calculation that I want to do now. Let's hyperlink over here to where we can do some work. And set things up. And you can see I've typed some stuff ahead of time to make this go a little bit more quickly. Here's the matrix. Do a control drag. Give it the name A. Use the context panel to get eigenvalues and eigenvectors. And you've seen that already. Repeated eigenvalue 2. So the algebraic multiplicity is 3. The geometric multiplicity is 1. We're short 2 generalized eigenvectors. How do you get them? Well, call them B2 and B3. B1 is the one eigenvector that you have. You've got to go out and find this vector B3, hit it with A minus lambda I, and that'll give you B2. And then you hit B2 at A minus lambda I, and that'll give you B1. That's what they say, but how do you find B3? That's the trick. So here's a Jordan form algorithm. Consider the null spaces of A minus lambda I to the k power, and call those matrices CK, and let MK be the null space of CK. So you have a bunch of null matrices which generate null spaces. And these null spaces arrange themselves in increasing order. M1 is a proper subset of M2, and M2 is a proper subset of M3. Now we're in 3 dimensions here, so M3 for us is going to be the whole space. So you've got to go out to M, you've got to find this M3, and you've got to select your B3 as a vector that's in M3, but is not in M2. Every book I've looked at, they use examples where they say, well, in this example, we can say this, but they never give you a recipe for guaranteeing that you can find a vector in M3 that is not in M2. It's always guess or gosh in the books that I've read and used. So this is what I'm going to propose. I found a way that I can guarantee that that happens. So you get that vector B3, you hit it with C, and that gives you B2. You hit it with C, you hit B2 with C, and that'll be B1. And the transition matrix Q that takes you into Jordan form has columns B1, B2, B3. Okay, let's start this algorithm. I'm going to re-execute a few of these commands so that you can see where things come from. So I've just reloaded the student linear algebra package. I want to reload the definition of A. Hit that single exclamation point. Okay, I want to define the matrix C, which is A minus lambda I, A minus 2I. But you don't have to put the I when this is a number. If it's not a number, then you need an A minus whatever I. Okay, so let's re-execute that. And here are the calculations of C, C squared, and C cubed on each one, I can ask for the null space, student linear algebra, vector spaces, and I can get column, null, and row. And this is where I get the null space from. So here the null space is M1. Here this is the basis for M2, and this is the basis for M3. I've given this a name because I'm going to come back to it. Here, C cubed is all zeros, so the null space is the full space, and this is the basis for the full space, I, J, and K. We need a picture. It's time for a first visualization. So in this picture, we see the three null spaces, M1, M2, M3. The black line is the eigenspace, M1. This yellow thing is M2. It's two-dimensional. The two green arrows are the basis for M2. The red arrow is the normal to this plane. It's a vector in the whole space. It's in M3, but it is definitely not in M2. No component is in M2. There's the secret of what I'm going to try to be doing. I'm going to find my B3 by looking in M3 for a vector orthogonal to M2. Now, Maple can find a Jordan form and a transition matrix that'll put A into Jordan form. And I've done the calculations here. Here's the matrix A, and this will show how Maple finds that Jordan form. Student linear algebra, solvers and forms, and you see there's a Jordan form command, and you either get the Jordan form or you get the transformation matrix. So here I've gotten the Jordan form, and here I've gotten the transformation matrix. I call it Q, and then I test Q inverse AQ, and it gives me back the Jordan form. So we could compare what Maple has done to what we're going to do. Okay, let's look at what Maple did. So a second visualization. So again, the yellow patch is a plane in which you see the black line here. That's the eigenspace. So that's M1. M2 is the yellow. Two green vectors are a basis for M2. The red vector is Maple's B3. C times B3 gives this blue vector here as B2. So that B2 lies in the plane M2. And C times B2 gives this blue vector here, which is along the eigenspace. Next, let's walk through the steps of my algorithm. So I start with this basis M2 for the null space M2. And I create a projection matrix. I'm going to call it P. So I can project onto M2. And we've seen in other examples how to do that. I give it the name P. Now, a general vector in R3, UVW. And I calculate the component orthogonal to M2, because this is the projection onto M2, and the difference is the component orthogonal to M2. So this is what that vector looks like, and each vector contains a UVW. So I evaluate it with UVW equal to 1. Each one is 1. And I get this vector orthogonal to M2. I call that my B3. It is my B3 in M3, not in M2. And then I have to calculate CB3. And I call that vector B2. And I calculate CB2, and I call that vector B1. And then my transition matrix is my B1, my B2, my B3, and this is what it looks like. And I call that Q. And I compute Q inverse AQ, and I get the Jordan form. So my computations are valid. A final picture, a picture of the vectors that my algorithm uses. Okay, so the yellow patch is M2. The little black line here, that's M1, the eigenspace. 2 green vectors are the basis for M2. The red vector is orthogonal to the plane. C times this red vector is this blue vector B2, which is in the plane, but it's not along the eigenspace. And C times this blue vector gives this blue vector, which is along the eigenspace. A final look at what Maple's Q is. Here's Maple's transition matrix. And I'm calling the column vectors beta 1, beta 2, beta 3, because they're not our B1, B2, B3. So this is beta 3. If we compute C times beta 3, we get this vector beta 2 right here. And C times beta 2 gives us this multiple of the eigenvector, which is here, beta 1. So that starting vector B3 can be more than just one particular vector. It just has to be in M3, not in M2. I think the simplest way to mechanize the finding of B3 is to take something that's orthogonal to the space below it. I think we had best end here. It's either any questions. If anybody wants these documents, send an email to me at rlopez@maplesoft.com. Ask for the material, and I'll probably send you a download link using your email as a way of locating you.